Organic photovoltaics, the future of transparent, flexible, and lightweight solar cells. Researchers are creating environmentally friendly organic photovoltaics, which provide many benefits over traditional silicon-based solar panels. A group of researchers is working on conjugated polymers to make carbon-based organic solar cells. Because of their flexibility and transparency, the organic alternatives can be utilized on surfaces that traditional silicon-based cells cannot, such as greenhouse glass, building walls, and even the sides of tents. Cells made of silicon are frequently large, heavy, rigid, and opaque. Crucially, their production is expected to be less costly and energy-intensive than silicon-based photovoltaics. Research on organic photovoltaics, OPV, increased between 2005 and 2015. However, interest in the topic has since declined, especially in industry. Among the several reasons are the lack of funding and the higher efficiency of perovskite solar cells, which may also be adaptable. Research on organic photovoltaic systems is essential and directly affects carbon neutrality. It is possible to use the so-called pi-conjugated polymers used in a laboratory to make solar cells that, like traditional solar cells, turn light into energy but are composed of plastic instead of silicon. The first pi-conjugated polymer was polyacetylene. Plastics are composed of long chains of repeating molecules because they are polymers. Pi-conjugated polymers are made up of carbon atoms that are alternatively linked by single and double bonds. Electron-containing pi orbitals that overlap and develop above the double bonds bind the single-bonded carbon atoms together. An electron in the neighboring pi orbital can migrate and create space in its native orbital when an electron in a pi orbital is destroyed through doping, according to the most straightforward explanation. This electron migration essentially turns plastic into a semiconducting material by creating an electric current. The organic photovoltaics developed by the study team using pi-conjugated polymers have an efficiency of 16 to 17%. Pi-conjugated polymers are being used by researchers to create organic solar cells. The goal is to supplement traditional silicon-based solar cells, which are becoming more and more efficient at turning sunlight into electricity in situations where they are ineffective or too difficult to utilize. Moreover, the pure silicon required for these solar cells requires a great deal of energy and intricate processing. Perovskite-based solar cells have been the subject of extensive study in order to remedy this. A crystalline substance, perovskite, can be thinly coated or printed. Although perovskite solar cells include the hazardous metal lead, they promise high efficiency on par with silicon-based cells. Therefore, more options are required, and one area that researchers are looking into is OPVs produced from pi-conjugated polymers. Similar to perovskite solar cells, the researchers use solution processing to create their pi-conjugated polymer-based OPVs. Compared to the heat-intensive procedure used to create silicon solar cells, solution processing uses a lot less energy. Consequently, thin polymer films can be used to print flexible products. Organic solar cells can therefore be incredibly light and flexible. In an OPV, the team's P-type electron-donating material is pi-conjugated polymers. They combine it with an organic fullerene-based, or more recently, non-fullerene, N-type electron-accepting substance in order to create an electric current between electrodes. However, the pi-conjugated, noodle-like polymers must be more crystalline in order to function effectively. In order to create a smooth channel for electron passage, the team attempts to determine how to stack and align them. They also concentrate on improving the miscibility, or ease of mixing, of the P and N-type materials. Attaining both high miscibility and high crystallinity simultaneously is quite challenging. However, obtaining high power conversion efficiency requires miscibility. In addition to creating OPV devices out of pi-conjugated polymers, researchers also investigate and work with their chemical architectures. The team's pi-conjugated polymer-based OPVs have an efficiency of 16 to 17%. Any lab's maximum efficiency is approximately 18%. Increasing the efficiency of his OPVs in the near future and eventually surpassing the current 25% efficiency of ordinary solar cells is one of the objectives. Additionally, they want a lower voltage loss in OPVs based on pi-conjugated polymers. The goal is to create OPVs that are affordable, lightweight, flexible, transparent, and effective enough to be installed on building exteriors. When energy must travel great distances from a solar field to a city, it is lost. However, what if transparent solar cells were positioned nearer to the site of need, such as atop agricultural greenhouse tops, building walls, or windows? Additionally, they foresee OPVs that might be set up on emergency tents to help people in need of energy during natural disasters like earthquakes and floods. OPVs based on conjugated polymers exhibit great promise. It will be difficult to get them to market. At least 5 more years are needed. However, the development of this significant technology will eventually be worth the wait, and the potential is worth further research, particularly from the business sector. When will they be mass manufactured? Organic solar cells are already being produced, but at relatively small scales compared to silicon-based solar panels. The timeline for true mass market availability depends on several factors. Current status. Pilot-scale production exists. Companies like Heliotech, Armor, and ASCA are producing organic PV films. Applications. Niche uses such as building integrated photovoltaics, BIPV, portable electronics, and indoor energy harvesting. Challenges slowing mass adoption. Efficiency. OSCs have lab efficiencies around 19 to 20%, but commercial modules are lower. Stability. Limited long-term performance due to sensitivity to UV light, oxygen, and moisture. Cost. Manufacturing is potentially cheaper than silicon, but stability issues drive up the cost per watt. Infrastructure. Lack of standardized production lines and industry adoption. Outlook. Experts expect broader commercialization between 2025 and 2030, especially in flexible, lightweight, and semi-transparent applications where silicon is less suitable. They may never fully replace silicon, but will likely coexist in markets that benefit from their unique properties. Could OSCs ever fully replace silicon? Theoretically possible, but practically unlikely in the near term. However, a hybrid model is more realistic. Silicon remains the best for high-power applications. OSCs become dominant in flexible, wearable, lightweight, semi-transparent, or integrated applications where silicon isn't viable. What are the most efficient organic solar cells? The most efficient organic solar cells, OSCs, are tandem devices using non-fullerene acceptors, NFAs. These cells have reached certified power conversion efficiencies, PCEs, of over 19% in laboratory settings, which is a huge improvement over earlier generations that hovered around 5 to 10%. Here's a detailed look at the most efficient types of OSCs. Top arrow 1. Tandem organic solar cells, 2 active layers. Efficiency, 19.3% certified as of 2023. How tandem cells stack 2 light-absorbing layers with different band gaps, so each layer captures a different part of the solar spectrum. Materials used. Front cell, wide bandgap donor, acceptor blend. Rear cell, low bandgap donor, acceptor blend, e.g. PM6, Y6. Advantages. Broader light absorption. Reduced energy loss, lower voltage losses. Atom symbol 2. Single junction cells with non-fullerene acceptors, NFAs. Efficiency, 18 to 18.5% certified. Breakthrough, the shift from fullerene-based acceptors like PCBM to non-fullerene acceptors like Y6 ITIC has revolutionized OSCs. Example materials. PM6, Y6, popular high-efficiency donor, acceptor pair. New NFAs like BO4CL, L8BO, and others are pushing toward 20%. Thin-film organic solar cells work by absorbing sunlight in an ultra-thin organic blend layer, creating excitons that are separated into free charges, transporting these charges through the donor/acceptor network, collecting them at electrodes to generate electricity. They are especially useful in flexible, lightweight, and semi-transparent applications with potential for low-cost roll-to-roll manufacturing in the future. Building construction, advantages of organic solar cells. Lightweight and flexible, they can be integrated into surfaces where traditional solar panels cannot go, like fabric, backpacks, or curved architecture. Low-cost manufacturing, they can be printed using roll-to-roll processes similar to newspaper printing, reducing production costs and energy usage. Semi-transparency, OSCs can be partially transparent and tinted, making them ideal for windows or aesthetic applications. Tunable properties. By modifying the chemical structure of polymers, OSCs can be engineered to absorb different parts of the solar spectrum. Electric plug uses and applications of organic solar cells. Thanks to their unique properties, OSCs open up opportunities beyond traditional rooftop installations. 1. Wearable electronics. Their flexibility and lightweight make them ideal for integration into clothing, backpacks, and fitness gear to power sensors or charge mobile devices on the go. 2. Building integrated photovoltaics, BIPV. OSCs can be built into windows, facades, or skylights due to their transparency and aesthetic flexibility, helping generate power without compromising design. 3. Portable power devices. Rollable solar chargers, lanterns, and tents with embedded solar panels are powered by OSCs in outdoor, emergency, or off-grid situations. 4. Agrivoltaics. Semi-transparent OSCs can be used in greenhouses to harvest solar energy while allowing sufficient light for plant growth. 5. IoT devices and sensors. They are ideal for low-power wireless devices such as sensors, smart packaging, and indoor monitoring systems, as they can operate under diffuse or indoor light. 6. Space and aerospace. Their lightweight and radiation resistance open opportunities for use in small satellites or space balloons. Construction challenges facing organic solar cells. Despite their promise, OSCs face several key challenges. Lower efficiency than crystalline silicon in commercial-scale modules. Degradation due to environmental exposure, moisture, oxygen, UV. Scalability from lab-sized cells to stable, large-area modules. Material costs and availability of some advanced acceptors and electrodes. Telescope future outlook. Research is actively pushing the performance of organic solar cells with tandem architectures, stacking cells with different absorption ranges, new donor-acceptor combinations, especially non-fullerene acceptors, improved encapsulation to enhance lifetime and durability, scalable manufacturing like roll-to-roll slot die or gravure printing. As materials improve and manufacturing matures, organic solar cells are expected to find widespread niche adoption, especially where traditional panels can be used, like flexible electronics, windows, and indoor power sources. Organic solar cells, the future of flexible and sustainable energy. As the global demand for clean energy accelerates, solar power has emerged as a vital solution. While traditional silicon-based solar panels dominate the market due to their high efficiency and long lifespan, a new class of solar technology, organic solar cells, offers exciting potential for lightweight, flexible, and low-cost energy solutions. These emerging devices promise to revolutionize how and where solar energy can be harvested, expanding solar applications far beyond rooftops and fields. What are organic solar cells? Organic solar cells are photovoltaic devices that use carbon-based, organic materials to convert sunlight into electricity. Unlike traditional solar panels that use crystalline silicon, OSCs utilize organic polymers or small molecules as the photoactive layer. These materials can be dissolved in solvents and processed using simple, scalable techniques such as roll-to-roll printing, making OSCs potentially cheaper and more versatile. How do organic solar cells work? Organic solar cells operate on the principle of the photovoltaic effect, similar to traditional solar cells, but with a few key differences due to the nature of organic materials. The operation involves 5 main steps. Light absorption. Sunlight is absorbed by the organic semiconductor, creating tightly bound electron-hole pairs known as excitons. Exciton diffusion. These excitons migrate to the interface between two materials, the donor electron donor and acceptor electron acceptor. Charge separation. At the donor acceptor interface, excitons split into free electrons and holes. Charge transport. Electrons and holes travel through different layers toward their respective electrodes. Charge collection. Charges are collected at the electrodes, creating a current that can be used to power devices. Most OSCs are designed as bulk heterojunctions, BHJs, a blend of donor and acceptor materials that increases the likelihood that excitons will reach the interface and separate effectively. Key components of organic solar cells. Transparent electrode, often made of indium tin oxide, ITO, allows sunlight to enter and collects electrons. Hole transport layer, HTL moves holes to the anode, e.g., petit PSS. Active layer, a blend of donor and acceptor materials, e.g. PM6, Y6, where light is absorbed and electricity is generated. Electron transport layer, ETL, moves electrons to the cathode, e.g. ZNO. Back electrode, usually aluminum or silver, collects electrons. Advantages of organic solar cells. Flexibility can be printed onto flexible substrates, enabling new applications like solar clothing or curved surfaces. Lightweight, ideal for mobile and portable power solutions. Semi-transparency, useful for solar windows and greenhouses. Low-cost manufacturing, scalable production through printing or coating techniques. Customizable colors, aesthetic advantages for integration into architecture and consumer products. Low-light performance, effective even in indoor or diffuse light conditions. Current efficiency and challenges. While OSCs have seen significant advances, commercial modules currently offer efficiencies of around 5 to 10%, while lab-scale prototypes have achieved over 19% in tandem structures using non-fullerene acceptors, NFAs, like Y6. Key challenges. Stability. Organic materials are sensitive to oxygen, moisture, and UV radiation. Short lifespan. Without proper encapsulation, OSCs degrade faster than silicon-based counterparts. Lower efficiency, still trailing behind silicon and perovskite solar cells. Scaling, efficiency drops when scaled from small lab samples to larger modules. Applications and uses of organic solar cells. Organic solar cells offer unique opportunities in areas where traditional panels fall short. 1. Wearable electronics. Integrated into clothing, backpacks, and smart textiles. Can power wearable health monitors, GPS trackers, or charge devices on the go. 2. Building integrated photovoltaics, BIPV. Applied on windows, facades, and skylights. Their semi-transparent and color-customizable nature makes them ideal for architectural applications. 3. Portable power solutions. Used in tents, rollable chargers, emergency lanterns, and other outdoor gear. Lightweight and flexible panels are especially suited for off-grid environments. 4. Indoor energy harvesting. Effective under LED or fluorescent light. Used to power Internet of Things, IoT sensors, remote controls, and wireless devices without batteries. 5. Greenhouses and agrivoltaics. Semi-transparent OSCs can generate power while allowing enough light for photosynthesis. Enable dual land use for farming and energy generation. 6. Consumer products and packaging. Integrated into e-paper displays, smart packaging, or interactive advertising. Help reduce the need for disposable batteries and low-power devices. 7. Space and aerospace. Ideal for lightweight, radiation-tolerant applications in satellites or drones. The road to commercialization. While companies like Heliotech, ASCA, and Infinity PV are already producing commercial OSC products, these are currently used in low-power or niche applications. Mainstream adoption will depend on overcoming issues like long-term durability, large-scale, defect-free manufacturing, competitive pricing against mature silicon and emerging perovskite technologies. However, the continuous rise in lab efficiency and material innovation indicates a promising future. Industry experts predict broader commercialization for mid-efficiency, 10 to 15%, OSCs by 2025 to 2030, especially in sectors where flexibility, transparency, or low-light performance are essential. Organic solar cells represent a transformative shift in solar technology, emphasizing adaptability, aesthetics, and low-cost fabrication. While they may not yet replace silicon panels for grid-scale power, they open entirely new categories of use, from smart clothing to solar windows and low-power electronics. As research continues to tackle efficiency and stability hurdles, organic solar cells are poised to play a vital role in the decentralized and diversified energy landscape of the future.